Okay, the mean. The mean is a measure of central tendency that is the arithmetic average. Now, that's one that kind of everybody knows, and you've all known this because it's part of the curriculum, Common Core curriculum. So if you grew up in that, if you were learning this from an early elementary school age, learning about the mean was something that they started to introduce and to increase people's understanding of, realizing that most people are going to learn the statistics route, and the mean is really the basis that people hear in modern day society, in literature, in journals, in newspapers, and people don't read it. I still get the newspaper every Sunday. Most people don't get that, but what you're going to hear in Vox News articles, if you call that news, or ABC.com, they're going to say the average person did this 6 times, didn't wear their mask 6 times in the last week when they should have. They're going to say average, and what they mean is the mean. It's a weird thing because we have this word that means the mean. But anyway, the mean is the arithmetic average of a group of numbers. And it's very helpful for us to collapse a giant group of numbers that we can't think of into one single number. And it kind of gives us a gist of, or a sense of, what the most common or frequent or likely thing to be is. And so the mean is the one that's used the most. It's also the one that mathematically we're able to do more with than, say, the median and the mode, in terms of taking descriptive statistics and using them to help us infer things about populations in the future or about which we have not measured yet. So the mean, this is the one that everybody knows. Now, you all know how to calculate a mean, so let's do it, right? We got 1, 3, 3, 6, 7, 7, 8, 8, 8, 9. Okay, we're going to do the math together. 1 plus 3 is 4. 4 plus 3 is 7. 7 plus 6 is 13. 13 plus 7 is 20. 20 plus 7 is 27. This one might be hard. 27 plus 8 is, that's right, 35. 35 plus 8 is 43. 43 plus 8 is 51, and 51 plus 9 is 60. So if we added all these up, they would equal They would equal 60. So 60 is the sum of x. X is just a word to describe the particular data that we're counting. And so we're counting up dreams here. So x just means any score of dreams that students could have. When we summed up x, we added them up. Sum is to add up. We got 60. So the sum of x equals 60. Now to find the average, we have to find out how many there are in our sample. So this is a sample, right? It's only 10 students. We asked 10 students how many dreams they had. We count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There were 10 students who were sampled. So our sample's size is 10. So now what we're going to do is take our sample size and we're going to divide the sum of x, in this case dreams, by our sample size. And that 60 divided by 10, I made this super easy, it's in the book, you can follow along, is 6. So we know the mean for this group of scores is 6. You guys good with that? Everybody understands it? Okay, so if that's fine with you, then great. I'm going to show you something else here that you might not be great with. Before I do that, let's do something fun. I'll show you my favorite data set. This is the favorite data set that I know of. It's just, I mean, there's so many groups of numbers out there. How exciting can groups of numbers be? Here, x. X just means whatever it is that we're measuring. So 2, 4, 6, 8, 10. It's my favorite data set. I love it. It's just great. We're going to use it a bunch, specifically when we get to variability, but I just wanted one more practice for the mean before I showed you the thing that's going to like kind of get you out of this. And we're calculating a mean first. This is easy. You know how to do it. We're just going to, well, we're going to sum up x. 2 plus 4 is, you can do this in your mind. I'll do it in my mind and then we'll see. So 2 plus 4 is, did you get it? 30. So that is the sum of x. We added up x. It's the sum of x. Now we're going to divide by the sample size. 1, 2, 3, 4, 5. That's 5. So 30 divided by 5, you guys probably know this by heart, is 6. So 6 is the mean. Question. Is 6 really the mean of that data set? The 6 that I circled? It's a trick question because while 6 is the mean of that data set, that particular 6 was a number in the data set. And if we didn't have that particular 6 in the data set, 6 would not have been the mean. And we can go over that in a second. Here's where I'm going to do something for the first time and you're probably not going to like it. But I do it this way specifically because, well, we've already just completed 2 examples, super easy, you know how to calculate the mean. That's not just what this class is about, is calculating the mean, but it's actually finding out what the mean is. And so I want to introduce you to something that's the formula for the mean. So bear down, I'm going to write letters and not in English. The mean is equal to the sum of x divided by the sample size. We just did this several times, so you shouldn't be freaked out by this. Even though it's letters, they represent things. So let's go over what they represent. Mean is represented by a lowercase m. That basically says that we're talking about sample, which is not the population. If you're doing population parameters, that would be a big capital M. Something else I want to show you. This is going to be a tough part of our class. Not everybody labels mean M. Sometimes people label it different things. They might have something like this, X bar. I don't know where that came from. The average of X? I don't know. Anyway, our class, we're going to go with M. M, mean. That's the abbreviation that we have for the mean. So the mean is equal to this thing right here. This is called sigma. Looks like a sort of a stick figure 3 or like a backwards E. It's a Greek letter, sigma. Sigma, well, this is the capital version of sigma in the Greek alphabet. Capital sigma means add up, right? It's telling you to add up. And you say, well, what do you want me to add up? Add up X. Okay, so this is how our book, this is how I represent X. X just means any of the scores in the data set that we're interested in calculating the mean for. There's other people that write X subscript I. I don't like it. It's too confusing. I don't like it. So we're not going to do that. But if you see that, X subscript I, it just means that any of the possible values of X that are in the data set. In case you want to get more comfortable with mathematical lingo. X, for us, means any of those numbers in our data set. So in my favorite data set, it was 2, 4, 6, 8, and 10. So X in that case is 2, 4, 6, 8, and 10. This says add up 2, 4, 6, 8, and 10. We did that. It was 30. This says divide. So we have 30, and we're going to divide it by n. N is the abbreviation for sample size. So in our case, 2, 4, 6, 8, 10, there's 5 x's in our sample size. So 30 divided by 5 equals 6. You know how to do this. You've just done it twice. We did it with dreams and we did it with my favorite data set. So this shouldn't bother you. All it is it's showing us how to complete the statistic of the mean, right? How do we calculate a number that represents the average arithmetically for the group? So now you know how to calculate the mean. You know the formula for the mean. But do you know what the mean is? Like, what would you say the mean is? Well, it's the arithmetic average. Yeah, what is that? It's the average. Okay, but you're using the word average. What is average? What does the arithmetic average mean? Well, it's that you add up all the things and you divide by sample size. No, that's the formula for the mean. What is the mean? Well, it's the average. You see, this sort of doesn't work for people. I'm going to share with you a definition, my definition. The mean does something very cool mathematically. It is the number that is numerically equidistant from all numbers in a data set at one time. Okay, so again, the mean is the number that is itself equidistant from all numbers in a data set at once. That doesn't make sense, because what if the numbers are far out? Well, let's use my favorite data set. We'll figure this out, what I mean by this definition. This definition is a difficult one because people don't think of the mean that way. They just think, oh, well, I know what it is. I know how to calculate it. But do you really know what it is? Do you really know what the mean is? Two, 4, 6, 8, 10. This is whatever we're measuring. Okay. 2, 4, 6, 8, 10. So these, oh, I'm all blurry for some reason. There we go. I don't know what happened there. I'm not a cameraman. I just teach at a community college, math. So 2, 4, 6, 8, 10. We already determined that 6 was the mean because we added up x, sum x, sigma x. We divided by n, which was 5. So 30 divided by 5 is 6. Also, this 6 is a part of the data set. The number 6, the mean of the group, is equidistant from all these numbers at once. What do you mean? Well, here's 6. How far is 6 from 4? Well, it's -2. How far is 6 from 6? It's not at all far, it's 0. How far is 6 from 8? Well, it's +2, right? 8 is +2 from 6. How far is 2 from 6? It's -4. How far is 10 from 6? Well, it's +4. So if we add up -4 plus -2, that's -6, plus 0 is -6, plus 4, or plus 2 is -2, plus -4 plus 4 is 0. That 0 means that the mean is in the right place. One of the principal functions of the mean is that it makes deviation scores sum to 0. Okay, again, I'm saying crazy stuff now. You're like, Professor, you just taught us the mean. We know how to do the mean. But now you're saying some crazy stuff. It's not that crazy. The mean is a number that makes itself at one time equidistant from all the numbers in the data set. For example, if I were to shift numbers in this data set, if I were to change numbers in the data set, the mean would shift correspondingly. Okay, so if we had our 2, 4, 6, 8, 100, well, the mean wouldn't be 6 anymore, would it? Again, we said that the mean makes itself at one time numerically equidistant from all of the numbers in the data set. So it's going to incorporate this giant lug right here. It's going to incorporate that and then make itself equidistant from that, which is really far away from these. All right, you guys want to do this? 2 plus 4 is 6. 6 plus 6 is 12. 12 plus 8 is 20. 20 plus 100 is 120. 120 divided by 5 is 24. So now we got 24 is equidistant numerically from all these at once. Well, how far is 24 from 8? Remember, 8 times 3 is 24. So 16. It's 16 less, minus 16. How far is 6 from 24? Well, it's just 2 more than 8. So minus 18. How about 4? It's just 2 more, minus 20, and 2 more, minus 22. How far is 24 from 100? Well, if you take 100 and you subtract 24 from it, you get... I'll wait for you. You thought I was going to say it, and then you'd know what it is. No, I'm waiting. You can do this, right? So you got 100. You're taking 24 away from it, right? If you took 20 away, you would have 80. And if you took 4 away from 80, you would have 76. Okay, so plus 76. If 24 is the mean, it will be numerically equidistant such that there is a balance point where the balance on one side of that number of 24 is equal to the balance on the other side of that number. So it is numerically a balance point for numerical weight. If these were weights, they would distribute evenly on either side of this fulcrum, that fulcrum being 24. So we have plus 76. Well, what is 16 plus 18? Plus 20 plus 22. I'll go the other way. It's a little easier. What's negative 22 plus a negative 20? That's negative 42. Plus 18? Well, that's negative, you could do it. 2 plus 8 is 10. 1 plus 4 is 5. Plus 1, so 60. Plus 16, negative 16, is negative 76. Numerically equidistant from all of the data points in a distribution at one time. What is the mean? The mean is a very helpful mathematical idea that when we group things together as samples, that there is a mathematical balance point. Let me show you another example of this. If you remember the number of dreams that those students had, right? We said that the average student had, what was it? 6 dreams a week? But it was based on data. They recorded from 10 different college students, and then we averaged that. And we said the mean was 6. The average dreams that somebody had was 6. The median is 7. So the mean is a little bit less than that. And the mode was 8. I'm using a balance here as this idea. And I said fulcrum because, well, I was a college diver, and that's the little bar that goes under the diving board. You push it forward to get a tighter board, and you push it further back to get a more loose board. But that's a balance point. That's where the weight is being balanced. And I was also in college, in high school too. I was a waiter. And this one time in high school when I was waiting tables at the Santa Clara Marriott, I had offered to help a friend out. She was in the weeds, and so I said, you know what, let me take the drinks out to your new table because it was just a 2-top. It had just been set, and she was having to deal with a big party. I'm like, I got your drinks. So I took my drinks and her drinks from the bartender. I'm going out holding those drinks, and this is when I learned about balance points. All right, so let's consider the data that we have from students' dreams. And we'll consider it like it was my tray. Okay, this is like my tray that I use to carry drinks on. And so I put a drink here, right? So this is 1. There's 1 there. There's 2. There were none at 2 position. Here's 3, 4, 5, 6, 7, 8, and 9. Now it'll make it better. Looks better now. So I'm sitting there balancing. I can't just balance that one. I got to put one over here because there's also 1 here, which is 9. And there's actually 2 here. And there's 1 here. There's 1, 2 here. There's actually 3 right here. And I'm fine. I'm balanced. What would happen, let's say if I'm walking, going to my table, I've got my friend's, her drinks on the back. And she comes and whoop, takes them from behind me. That's exactly what happened. I dumped those drinks all over the businessmen sitting in their business suits at lunch. Yeah, most waiters or waitresses have been, oh, I'm sorry, what do we call it? Servers. Excuse me, we change names of everything now. Most servers, actually no, I was a waiter. That's what we called it back then. I was a waiter, there was nothing wrong with that. There was nothing wrong with waitresses then. I don't know why there are now. And there are men and women. So when I dumped those drinks all over those business people, they experienced my lack of balance. And that's when I learned that balance occurs. It seems like there's far less weight over here, doesn't it? But if you look at where my hand is balanced right here at a fulcrum, right at the number 6. So if you imagine, here's my hand. This is a bad hand drawing. So here's my hand that's balanced, holding those. You might say, hey, it looks like it's really shifted far that way. It's the balance point because numerically, if each of these blocks, or let's say drinks, were balanced correctly, if you took any of them off, it would upset the balance. And so you would have to, in order to not dump those drinks on the business people in their suits, sitting at lunch, probably going to some important meeting afterwards. Oh, that was so embarrassing. You would want to shift your hand. You'd want to shift it. So which way would you shift it if your friend came up and she grabbed this drink? Which way would you have to shift your hand to stay balanced? You'd have to shift it that way, right? Because here it's balanced, but if you took that weight off, you'd have to shift it this way. So my prediction is that if we take the 9 off, the numeric shift will go this direction so as to stay perfectly balanced. Now, how do you do that? Numerically, we know that when you added up those numbers, when it looked like this, that added up to a weight of 60. If we take away the weight of 9 from 60, you get 51. Also, how many drinks are there? 1, 2, 3, 4, 5, 6, 7, 8, 9 now. There's no longer 10 drinks. So if we divide 51 by 9, watch this. Okay, Google, what's 51 divided by 9?
The answer is approximately 5.666667.
Whoa, very, very accurate. I wonder who told her to round that way. Anyway, 5.6, basically 5 2/3. So 5, and then if we divided this into 2/3, it would be 1 2/3. So you got to move back just slightly for that. Okay. Well, what if she didn't take that off? What if she came and instead of taking off this one, what if she took off that one? Would you just have to shift 1/3 the other direction? It seems so, but it's not. Watch. The distance from 6 to 1 is a lot further than the distance from 6 to 9. So it's going to have a more dramatic impact because of its distance numerically away from that center point, that fulcrum of balance. So when she took the 9 away, we just had to shift a third of the way towards 5. But what's going to happen when she takes 1 away? She comes by and bloop, grabs that drink. Well, now let's calculate it. Instead of having 60, we have 1 less. 59. Also, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 drinks left on our tray. Okay, Google, what's 59 divided by 9?
The answer is approximately 6.555556.
Okay, so let's just say 6.6. Now, instead of going 1/3 there, I have to go more than halfway to 7. I have to shift more dramatically. And the reason that I have to shift more dramatically to stay balanced is because 1 is so much farther away from that center point of balance than 9 was. You'd think that 9 being more, right, a bigger number, would do a bigger thing to it, but it's actually relative distance away that changes things more dramatically. So I hope that this gives you a sense really of what the mean is doing for any distribution, is that it's making itself at one point numerically equidistant from all of these, in our situation, drinks. In most situations, just whatever it is that you're measuring. So what do I mean equidistant? 6, which is our balance point here, how far away is it from 1? Well, let's do it. 1, 2, 3, 4, 5. So 1 is -5. So it's a -5 pressure on the left, right, on the lower end of 6. How far away is 3? Well, it's 1, 2, 3. So it's -3, but there's 2 of them, right? So that's double the weight at 3. So that's double the negative or downward pressure. So together on the left side, in this case, or the lower end, there's an 11, a -11 downward force on the thumb side, right? But on my finger side, do you think that there's that same 11 that's counterbalancing it? Because that's what the mean does. So let's measure it. How far is 7 away from 6? I mean, it's only 1, right? 1 away, so +1. Well, but there's 2 of those. So that's +1 and +2. So there's really +2. How far is 8 away from 6? It's only 2 more than 6, but 1, 2, 1, 2, 1, 2. We had 3 of those. And how far away is 9 from 6? It's 3 away. 1, 2, 3. +3. So it seems like -11, is there that -11 counterbalance with a +11? We'll count it up. 1 + 1 is 2. 2 + 2 is 4. 4 + 2 is 6. 6 + 2 is... Why did I write a 3 there? Excuse me. 8s are only 2 away. 6 + 2 is 8, and 8 + 3 is +11. So here is a balance, here is my balance between -11 and +11. It's right there. If I change things, then I'll have to shift to make sure that I don't drop these weights. To know that I've learned my lesson, I'll have to ensure that I'm always at the mean of that center of balance. So numerically, the mean is that balance point between both sides in a distribution. If anything changes about that distribution, well, then you've got to shift yourself either way to compensate for it. As you can see, the mean is very responsive to any changes in the data. If this was like a median, it's not so responsive.